Good afternoon. This is our lecture number 22nd and supposed to be our last lecture. Previously, Ajahn already reviewed you about the task, the frame, drawing the shear diagram and moment diagram, friction, and the centroid. And Ajahn asked you to focus on the task, the frame, and the centroid. And also, since you are the CE student, the shear diagram and the moment diagram also important, but it will take a long time for the examination. And this is another important one. Since you are CE student, you got to know the property of the section. Or even you are the polymer engineering, if you use the polymer to produce those kind of structural section, you got to know, you got to have the concept of the centroid and the moment of inertia. Now, we come to the moment of inertia of the composite area. And Ajahn should say the structural steel. Ajahn should mention about the structural steel. The structural steel section produced by many steel companies such as Siam Yamato Steel, the BSBM, Bang Sapan, Bang Mill. The steel industry in Thailand costs more than 100,000 million baht a year. We use a lot of steel in our construction. And the structural steel have section, and the section of the structural steel can be I, can be P, can be box, can be C. C is like a cut box by half, and can be L. All of them are important structural steel section, and as you may expect, they are always in our final examination. How to compute the moment of inertia of the composite area? We start with the simple area. And if you may notice on this one has rectangular section, has rectangular section, and has rectangular section. This means what? Composite area composed of simple area, especially the rectangular, because rectangular is the simplest section to produce structural steel section. Or polymer engineering, you may know the word of FRP, fiber reinforced plastic. Or sometimes it's not only fiber, fiber reinforced plastic. If you put it in the word CFRP, that's going to be carbon fiber reinforced plastic. Again, material is aluminum, steel, carbon fiber. Most of this structural section composed of simple rectangular section. Now, let I take you to the simple rectangular section. Most of the time, we said the width of this one is B, and then the depth of this one is H. The section we have the axis. This is x-axis, and then this gonna be y-axis. And if you may notice the beam, you go outside the beam, we have this kind of section. We won't make the beam in this kind of section. The problem of this is what? This section if this H to be 10, and then the depth gonna be 2, so you will have the I sub x of this one 10 times 2 square divided by 12. This is going to be what? 40 divided by 12. Let's say centimeter powerful. However, with the same section over here, I sub x about this one, B is going to be 2 times 10. Sorry, this is going to be power 3. This is going to be power 3. That is going to be 80 divided by 12. This is 2. B is 2. And then H is 10 times 10 cubed over 12. This is going to be 2,000, right? 2, 1, divided by 12. That's very huge difference. That's why in our practice, you will see the beam putting in the position with this kind of rectangular. Now, we have this kind of section, for sure, the beam follow this kind of engineering section will have the ratio of I over A high. Higher than what? Higher than rectangular. So many times we have this kind of section, and again, they are going to be your final examination. And in short, for the beam that has this kind of section B and H about x-axis, I sub x gonna be BH cubed over 12. And if you put it in this y direction, you will have I sub y equal to this one, H times B cubed over 12. Most of the time, we will find that I sub x is larger than I sub y. Therefore, the section for the beam going to be something like this one. Now, let me move you another thing. We have the axis here. This is going to call the section axis. I should call this one section axis. And we also has this kind of axis. This is going to be small area axis. In typical one, we may determine the I about this x-axis. Again, following this equation, you may have I sub x equal to this one, H B cubed over 12. However, this time, the centroid of the small area is over here, but the centroid of the section is here. That means typically the centroid of the small area different from the centroid of this area. Then, if you prefer to determine the moment of this area about this one, you got to add more term. You got to plus A, and then this is going to be this distance in y direction. We call d sub y times d sub y, and then square. This is going to call upon the parallelogram. It's called parallel theorem. And then you don't care about the theorem. You care about how to use it. Now, let me talk you through this is 3 homework, and this is the real structural section. Thinking about this one, This has what? This has I or W section. And this gonna have L section. This gonna have hollow section. And again, this has the L section. Okay. And there are, this is going to be rectangular hollow, rectangular section. And then this kind of section you may use for building factory, building your home, maybe in the future, but not popular now. We didn't like use to in our home. So in short, this called structural section. It can be steel, it can be aluminum, it can be fiber, reinforced plastic for polymer engineering. And we produce this, since this kind of section are high performance section. Why is this high performance section? Because it has I over A ratio. It has the large value of moment of inertia or cross-sectional area. Coming into this equation where Ajahn like to have large I is over here. This term is for moment of inertia, your friend. Now study mechanics of material and we compute for the deflection. Okay, if you put the line across this one, you can see this is going to be what's so-called the fraction or specifically is called vertical deflection. Do we like to have this one large? No, we don't have to have this one large. We're going to be like to have small, or we like to have it really small. Okay, so since the equation is deflection equal to force length cube divided 48 EI, the divider must be large in order to produce small deflection. Okay, then the I section is going to be good. Okay, the best compared to this one, and then compared to this one, the number one gonna be better than number two and better than number three. Now, following this one, Ajahn show you this beam. Okay, Ajahn put the the paper and then make it the beam. The I section has this one to be I sub x and this one to be I sub y. Is better than this one. Is better than this one because this one I, if this is x, is going to be 10 times 3 cube over 12. That's going to be 10 times 27 over 12. That's 270 over 12 centimeter powerful. However, if we put it in this direction, I sub x gonna be 3 times 10 cube over 12. That's gonna be 3 times 1000 divided by 12. That's gonna be 3000 divided by 12. That's gonna be larger. And believe me, this I sub x, we have it later. Okay, gonna be a lot bigger than this one. Okay, but the calculation for the I section gonna be a bit tougher. And then most also the beam, the support like this one. Since this has I sub x, okay, and this one gonna be I sub y, and I sub x always larger than I sub y. So the deflection of this one, if the load is the same length, the same of V1, gonna be larger than the deflection over to V2. Then we come to the steel table. On the steel table, this is the name of the section. This is going to be the weight per kilogram. It's about you, right? 44 kilogram per meter. This is heavy, right? 44 kilogram. This is going to be the depth. This is going to be the width of the flank, the thickness of the web, thickness of the flank. We don't interest that's what we come over here. I sub x always larger than I sub y. This is 6 times larger. Again, that's why we set up the beam in this manner. We don't put it in this manner because the I over here is I sub x larger than the I over here. I sub x larger than I sub y. Now, coming into the concept of moment of inertia, we start with mathematics. Okay, mathematics. Sometimes engineer won't okay. we cannot go away from math because what we are learning here, even chemistry based on math, physics based on math, biology sometimes also based on mathematics. By the definition, moment of the area is the second moment of an area. So we got to have the term I equal to BH, time H square over 12. This is the area, and then the area has the moment. So the first H is going to be moment arm, the first H. But it's second, so it's going to have moment arm square. So this term actually is moment arm square divided by 12. And mathematically, this is going to be millimeter powerful. B is millimeter. H is millimeter. H square millimeter. Centimeter powerful. Meter powerful. By the definition of mathematics, actually we don't care about it, but you got to go back about very small element dA. So differential of I sub x is going to be moment arm, the same as Ajahn put it over here, moment arm, time the area, dH, time the area, and then you got to do the integration for determining I sub x. So finally, we have this type of equation. Since you got to integrate it to determine this small area. Now, the same thing. This is going to be the moment of inertia about x-axis. So you got to time by the y. It's going to be moment arm, and then second, it's going to be moment arm square. Now, for I sub y, things are a bit different. We got to think about the same area. Time moment arm. This is moment arm is x. Second moment, so it's going to be x squared. And in short, if you're trying to determine the whole area, you got to do the integration. The word integrate means combine. That means you combine all of the term x square dA to produce the whole section. Don't worry, it is mathematics. Come to important another one. J called polar moment of inertia. J gonna be I sub x plus I sub y. You're going to have this one in chapter 5 of mechanics of material. But don't worry now. We won't care about scale yet. Now, coming to the parallel theory. Since Ajahn already mentioned following what we have here, okay, we will have moment I sub x. If this one B, this one H, this one V sub x equal to B H cube over about the axis passing through the centroid of the section. Remember this equation. Now, you have another axis that's going to be about this one called y. And then you have I sub y equal to, now, this one change to h times b cube over 12. Okay. Now, again, put it to another aspect. If there is an axis over here called x palm, now we will determine I sub x palm plus equal to I sub x, this term, I sub x, and then plus a b, this is in y direction. We call this b sub y in y direction, distance in y direction square. Now, this one going to change to what? B times h cube over 12 plus b h area and times b sub y. Since this is going to be h2, okay, it's going to be h over 2 and then square. Now, Ajahn have the term I sub x, but this time x palm, okay, another axis, I sub x palm, gonna be b h cube over 12 plus b h square over 4. Okay, so we have this one 1 over 12 plus 1 over 4 b h cube b h cube. This one to be b h cube over 12. Hey, Ajahn, putting it in the x palm direction, we found I sub x palm larger than I sub x. And then previously, we know that there's I sub x larger than I sub y. So the concept comes, okay, putting the area out of its own centroid axis will help. Then we come to the I section. Okay, again, Ajahn should say again, this is going to be structural steel. Okay, talking again with this area. Okay, we put this area far away from the centroid of the section. However, this area has its own, this one. Okay, and then let's call this one x. Let's call this one again x palm. I sub x palm equal to I sub x plus AD sub y square. Ajahn notate the same thing. Yes, Ajahn confirm your knowledge that I sub x is only moment of inertia about small area. But you can increase the moment of inertia by putting it, locate it far away from what you like to have. Now, that's called parallelogram, parallel axis theorem. Okay, if you prefer to determine moment of inertia of the area with respect to this axis, far away from the axis, passing the centroid of the small area. Okay, you put it again now. You got to time small area with the moment. Okay, this is moment arm. That's gonna call the total green area is gonna be y. And then y is going to be y palm plus we have over here v sub y. Okay, after you do matrix integration, manipulation, those kind of at the end, we have this equation. We will use this equation. Okay, moment of inertia of the axis that far away from the centroid of the small area equal to moment of inertia of small area plus the area times moment arm d sub y square. So that's going to be the basis for I sub y. You will have very same equation, but change what อาจารย์ change this one to y, change this one to y palm, and the distance now going to be d sub x square. Okay, we have composite area as อาจารย์ mentioned. This one composed of 1, 2, 3, 4 color. This can divide into 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is called traffic barrier. If you go to Terminal 21 now, there are construction, there are some traffic barrier. Traffic barrier is one of what's so-called the cross-section composite area, which is cross-section area of various structural member, various 8 of them. Okay, it's formed by plus or minus this one plus. Okay, for simple area such as rectangular as shown here. Okay, and now we will be able to determine y bar. Y bar is the location of the centroid of the composite area. Okay, so if we like to determine the moment of inertia of the area, we got two bases on this axis that's passing to the centroid. Now, we have very important rectangular area, and Ajahn would like you to remember it. And Ajahn would like you to solve this problem to get 5 points. Okay, the same as the centroid. There are important equation. I sub x. This one, I sub x is here. It's going to be b. It's going to be, this is b times what? H cube over 12. Then that is about x-axis. Now, if you looking for the y-axis, this is going to be our y-axis. Now, the equation is h, this h, times b cube over 4. Okay, it's a bit different, and I sub x larger than I sub y. No, this one is not. This one, you got to have the different thing. You got to have I sub y larger than I sub x. Okay, this one I sub y is larger than I sub x. And then if you prefer to determine I sub x palm, okay, you have moved from the centroid. I sub x palm going to be I sub x plus the area times this one times d sub y, in which is going to be h over 2. Then you have this one h cube plus this one a h 2 square. We have this one. For sub y also, we have I sub y following this form. This is about this axis. If you prefer to determine it here, I about here is going to be I about axis and then plus the area, the same area, but the moment arm change into this one, the sub x. This is going to be the sub x in x axis, and then it's going to be b over 2. And then you put this one, change this one to b over 2, and then you get the result. Okay, you get the result. That's going to be hb cubed over 3. This is bh cubed over 3. Okay, if b is 10, again, h is 2. This is going to be 10 times 2 cube over 12. That's going to be 80 divided by 12 centimeter power 4. This is going to be h2 times b cube over 12. That is going to be 2,000 divided by 12 centimeter power 4. That's huge difference. Okay, so we got to produce composite section. Many area, luckily, for now on, for this course, we were taking care of the circular semi, circular quarter, circular. You may use it later when you go to work. Okay, now it's time for example. Okay, I can conclude the equation over here. That's important for you to follow it. Okay, let me stop the first section. Here we come to very important structural section. Okay, there are papers over there, and this is going to be the section of maybe I section. Also, we may call it W section. They are close to what kind of it. This one actually not the I section. For the I section, it's going to have this kind of shape. But for W section, is have this kind of shape. W is from the word of Y frank. Okay, so the Y, the width of the section gonna be close to the depth. But when we talking about the I section gonna have this one to be B sub F. That's gonna be less than D. And typically it's maybe only D equal to D 2. Now, we have the section, and then this section is special. It is double symmetry. This section is double symmetry. Again, how come you call it? Since this is an axis, spiral-axis, the top and the bottom, they are the same. If you divide it by this axis, again, the same. So there are two axes of symmetry. We call this section double symmetric. Okay, double symmetric section. Now, we are looking for the moment of inertia about NA. Again, it's not an X, it's called NA. NA is important for beam. Okay, for the beam, there is the axis where the stress equal to 0. Okay, if you bend the beam like this one, on the top is compression, bottom is in tension. The same. Top compression, bottom tension. They are the middle of this one. That has no force.
and then there going to be no stress. Now, we are looking for the section with double symmetry. So, the centroid, okay, C going to be the centroid of the cross section. This is important because we also need to determine the centroid of the small, or อาจารย์ call it the segmental area. They are different. Okay. First, อาจารย์ separate the area like the composite. This is going to be our first area, and then this is going to be our second area, and then this is going to be our third area. Okay, the moment of inertia about neutral axis will be the moment of inertia of the first one about neutral axis plus the moment of inertia of the second one about neutral axis, and then plus the moment of inertia of the third area about the neutral axis. Okay, now let me put it over here. I of this one, we start with the first one. It's going to be the area over here. Following the picture, you will see the width of this one gonna be 250, and the thickness of this one gonna be 20. Okay, if อาจารย์ put it bigger than this, it may help you. Let me put it like this one. Okay, and then put it like this one. Sometimes if the picture is not clear, it's better to draw it by yourself. Okay, this is going to be the same section. This is going to be the NA axis, and อาจารย์ again start with this one, and อาจารย์ put this one to be this one 250 millimeter, and this is going to be 20 millimeter. The first area has the centroid over here. Okay, that's going to be different from the centroid of the section. Now, the first one over here has this axis. Okay, so the first term we have I(n/a1) gonna be I. Putting into this one, y1 about its own axis, and then plus a, and then it's gonna time this one b sub y1 b sub y1 square. Okay, now start by this one. It's going to be this term 250. Okay, time what? Time the thickness cube time 20 cube, and then divided by 12 is about its centroid. Then this one has the area of what? Plus term A is gonna be 250 times 20. Now, thinking about this d sub y, the problem said from here to here. Problem said from here to here is 150 millimeter. Then this is going to be half of the thickness. This is going to be 20 divided by 10. That's going to be, sorry, the 2. It's going to be 10. So the same distance from here to here going to be 150 plus 10. Okay, you have this one for 160 and then AD square. Okay, all of this gonna be millimeter powerful, powerful. Now, come to the second one. The second one is gonna be this area. This area. This area has its centroid the same as the cross-sectional area. That's gonna have this axis, okay? That's gonna be on top of the NA. So this 10, this 10 d sub y gonna be 0. So basis upon this one for the second one. Plus, we have this one 20. Following this one, it said this is 20 millimeter. The depth, the total depth, 150 and 150 gonna be 300. So it's gonna be 20 times 300 cube over 12. And then plus A times 0 square. The centroid of the small area is the same as the centroid of the cross section. Now, coming back to this one, okay, this area this is 250 millimeter and thickness is 20 millimeter. So the moment of inertia about its centroid gonna be plus 250. And then we have this one 20 cube over 12. And then plus the area gonna be 20 times 250, 250 times 20. And then we have the distance from here to here. And you may notice that the distance from here to here, the black and the red, they are the same. It's going to be 160 square. So, in short, you put everything in your calculator, you should get 301.3, 10 power 6 millimeter power 4. Okay, that's going to be the answer. Sometimes Ajahn not only asks you in millimeter, he may ask you in meter, and Ajahn should say in practically 1 meter. 1 meter equivalent to 1,000 millimeter. Now, if you put it in power 4, okay, in power 4, you will have this one, 1 meter power 4 and 1,000 millimeter power 4. So 1 meter power 4 gonna be 10 minus 12 millimeter power 4. If you prefer change millimeter power 4 to be meter power 4, you got to put this one I sub NA equal to T01.T 10 minus 6 divided by 10 12. Okay, to change this one to meter power 4, and then this is going to be 301.3 10 minus 6 meter power 4. Okay, now if you would like to do for the other axis, for example, if you prefer to determine about this axis, Ajahn put this one, let's say this one gonna be sub y. Okay, basis upon this one, you got to do sub y equal to I sub y 1. plus I sub y. This is going to be number 2. And then plus I sub y number 3. But this one, everything must follow the axis y. Okay, over the axis y. And you can see the location of the yellow. The location of this one actually is green. And the location of the orange, hey, Achan, all of the location of the area, they are putting in the same location of the fourth section. This is good because this is going to help you for the calculation by putting on this one. You will have the first one. The first one is here, 20 times this one, 250. 20 is here because it's going to be about this axis. 20 times 250 cube over 12. And then for this one going to be this width plus this is what? 150. 300. It's going to be 20 cube over 12. And then for the last one, over here, you may just times this one by 2, or this is going to be 20 times 250 cube over 12. You will get this one in millimeter power 4. I will make this one for you guys to put it into your calculator by yourself. Okay, and you will see m/NA will be larger than I sub y. Okay, this is going to be our first example. Now, let me put it into a bit more complicated. Okay, this one is the section. That has what? That has the top flank smaller than the bottom flank. So this kind of section, we call it only one axis of symmetry. This is going to be only one symmetric axis. Okay, and then following this one, again putting this one for x-axis and this one for the y-axis, and then following what we have learned from the previous chapter, we're going to have this kind of reference axis. If you would like to determine reference axis, the y bar, okay, the y bar, okay, you should be able to measure the y bar going to be the distance from here and then up until here. The center is over here. Then following again, what we have, this is going to be y time. This is going to be x time. Okay, this is going to be the center of the section. And if you measure from here to here, this is going to be x bar. If you measure from here to here, it's going to be y bar. Okay, to understand the section, you got to be listening. Due to the symmetry, we can determine y bar easily because it's going to be symmetric about this one. So basis upon this one, you may see the width gonna separate into two half. We may get x bar equal to 600 divided by 2. You get this one to be 300 millimeter. Well, again, that's easy. Yes, it's easy. Okay. How about y bar? Y bar gonna be summation of AI. Y I and then divided by summation of AI. There are three area, three area. Okay, there are three area. If I can put it, this is 400. Let me put this one 2 centimeter, and then this is gonna be 100. Put it in 2D. It's gonna help you. This is gonna be half. This is gonna be 100. Okay, the weight gonna be 100. So half. So the depth 600 gonna be 3 centimeter, 3 centimeter, and this is gonna be 1/2 over here. 1/2 over here. 600 millimeter change to 3 centimeter. This is going to be your section. Okay. Now, make it a bit simpler. This is going to be the center. And again, this is going to be your reference axis. And this is going to be your y bar. Okay, y bar. X bar, we already determined it. That's going to be 30 millimeter. Now, we got to separate the section into 3 areas. First, okay, and then second, and then third is going to be here. To determine the center, it's better to put it in the table. We have segment, okay, and following this one, 1, 2, and 3 segment. We have segment over here, 1, 2, and 3. Now, versus on this one, we have the whole AI. Okay, AI is supposed to be the starting point because AI on the top and AI also on the bottom. So AI millimeter square. The first one over here. We have this one for 400. We have this one for 100. So therefore, it's going to be 400 times 100. You got to have this one for 40,000. Okay, 40,000. Then, following the second one, this is 100 millimeter. Again, you put it, this is going to be 100. The depth going to be 600. From here to here is 600. So 600 times 100, that's going to be 60,000. And then for the last one over here, this is going to be 100 millimeter. And then putting this one to be 600. Okay, if you want to put the unit, you may say unit in millimeter. That's going to tell Ajahn you understand about it. So it's going to be 600 times 160,000. Now, in conclusion, we do the summation. This is 46. It's going to be 3,000. That's going to be summation of A sub I. Okay. Now, move to the term YA sub curve. Okay, YA sub curve. This is going to be yi sub curve, the centroid of each section. Okay, the centroid of each section, that's going to be in millimeter. Okay, and then you got to have this one. The first from here to here, from here to here, that's going to be our yi curve. The first one, that's going to be what? This is 100. This is 600. This is going to be 100 divided by 2. Then this is going to be 6, 7. That's going to be 750. And then the second one, somehow going to be half of this one. Okay, this is going to be the centroid of the second one is going to be combined of this one. That's going to be half of this length, 600 divided by 2. And this is 100. So this is going to be the distance for the second section is going to be 300 plus 100, 400. The last one going to be simplest one from here to here. 3 curve. This is in combination y2 curve. And this is going to be y1 curve. Okay. And then for this one, half length going to be 50. Then times this one by this one, you get, wow, 30 million. This is going to be 30 million. This is going to be some AI, yi curve, millimeter powerful. This one going to be, that's quite a lot. Yeah, 30 million. 30 million. Yeah. And this one times this one, 20, it got 24 million. Okay, the last one, this one times this one, going to be 30. No, it's going to be only 3 million. Okay, this is going to be 3 million. Summation of AI yi curve. You get this one to be 57 million. Okay, and then you have this one to be 57 million, and then divided by this one, 160,000. This millimeter cube divided by millimeter square. You have this one. Wow, what happened? Huh. Okay, what happened? This is going to be in millimeter, and we got it 356.25. Now we have this one 356.25 millimeter. This is 356.25 millimeter. Now they ask us to determine the I sub x and I sub y. Okay, don't worry. Typically, Ajahn will separate this problem into 2 problems. Okay, this one going to be for the centroid. And then if they ask you to determine I sub x and I sub y, believe me, that's going to be another problem. And Ajahn will provide you with the y bar. And also you got to know for the x bar by yourself. Okay. Now, the problem is going to be a bit complicated. Let Ajahn do the same thing. Okay. Put this one for the first and put this one for the second. For the second, this one and this one for the second. And then I put this one for the third. Now, we going to determine moment of inertia about x-axis. About x-axis. Okay, we have three areas before. One, okay, two, and then three. About this one gonna be the centroid of the section. Now we got to start from the first one. We got to start from the first one. I sub x equal to this has this one. It's gonna be in combination of I sub x prime about x prime axis plus I sub x1, I sub x2, and then plus I sub x3. Let me zoom it in because we don't use the information over there. Then for the first one over here, you got to compute for this term. Okay, mark it. This is centroid of the segment, and that's gonna be equal to what? This is 400. This is 100. 400 times 100 cube over 12 is rotated about its axis. Then there are the distance, okay, eccentric distance from here to here. Plus, this is the sub y1. Okay, this is only the sub y1. Who got to determine this is going to be our 356.25. This is so. We determine it. Okay, we got to what? We got to determine the distance from here to here. From here to here is going to be 600. 600. Okay, and then from here to here, you have this one. You have this one to be 100 divided by 2 is going to be 50. From here to here is going to be 100. So actually you have 750. Okay, so this is going to be 750 divided by y bar to take care of d sub y bar. Okay, slowly. Plus A. This is going to be A. The area of this one. Gonna time d sub y prime square. This is going to be the term d sub y prime square. D sub y prime measure from this one to this one. Y bar measure from this one to this one. Then this is 100 thickness. And this is 600. And this is half of the thickness. So the total here is going to be 750. Okay. And then 750 measure from here to here. And this is y bar minus y bar and square. Okay. Minus y bar and square. Y bar. This is going to be y bar. Now, for the second one, plus for this one, this is 100. 100. Total here is 600. 600 cube. And then divided by 12. This one by 12. And then the area 600 times 100. And then times the distance. This is going to be the centroid of this area. And you're going to have this one this one moment of inertia about this batches area. And then the distance from here to here, okay, A times D, this one, D sub Y2. This is going to be D sub Y2 square. Okay, D sub Y2 square. What is this? What is this? Now, from here, measure up until here. Measure up until here is going to be 300. And this is going to be 100. The total from here to here is 400 minus this one. You got to have D sub Y. Okay, let me put it. This is going to be 400. Okay, and this is going to be your Y bar. And then you can determine this distance. So it's going to be 400 and then minus Y bar. I put Y bar because I won't have space to write it. Okay, it's going to be 356.25. Now, the third one has the centroid over here. Okay, and has the axis here. The third one has this one for 600. The thickness is 100 times 100 cube over 12. Then the distance from here to here gonna be D sub Y number 3. This D sub Y number 3. The area 600 times 100 times this D sub Y number 3 square. So this is simple, Ajahn. Sure, this is Y. Okay, Y bar. That is Y bar. And this is half minus 50. Okay, Ajahn put it again. This is gonna be Y bar. And then you subtract only this small element. Okay, you get this one. So in total, you will get I sub x equal to 313.800 and then 10 minus 6 millimeter power 4. Okay, that's going to be huge number. And if you prefer to change it to meter power 4, 13800 10 minus 6 divided by 10 minus 12, 13800 10 minus 6 meter power 4. Okay, the same reasoning. That's why we divide it by 10 power 12, because 1 meter, 1000 millimeter, 1 meter square. This one power 4. This one must be power 4. This is 10 power 3. Power 4 is going to be 10 power 12 millimeter power 4. Okay. Very small compared to this one. Okay. Then you have another one. We have I sub x. They said in millimeter 13800 10 power 6 millimeter. Now, I sub y. Okay, I sub y. That's sub y. You may draw another pictures, and I recommend you to draw it. Okay, draw another picture. This is half. Okay, and then 3. This is 3 centimeter to represent 600 millimeter. And then this one, 600 millimeter for 3 millimeter. Now, we are determining for this y-axis. This y-axis. And then this is going to be our first area. Okay. And then I sub y. I sub y equal to I sub y number 1 plus I sub y number 2. And then plus I sub y number 3. Okay. This one, we have this axis. And then this axis passing through the y. So, in short, we have this one 100. We have this one 400. About this axis 100 times 400 cube parallel. And since the center of the section on axis y plus 0. Now, let me move you to the second area. Okay. On the second area, you have this one to be the center of the area. Now, this is 600 and the thickness over here is 100 plus the second one. 600 times 100 cube over 12 and then plus 0. The location of the center of the segment, the axis. So there is no eccentricity. Okay. And the last one over here. Over here also the same. The axis also plus this is 100. And then this is 600 cube. And then divided by 12. Okay, for the third one. And then since the center, the segment on top of the y, so we just plus 0. Well, then this is simple. Yes, this is simple. If you like to determine I sub y, that's gonna be 2,830 10 minus 6 millimeter powerful. Okay, very simple. I believe you should get full score on this one. And at the end, we have this 2,830 10 minus 6. And you can see I sub x larger than I sub y. When you construct this one, we will put this one on the structure. Okay, will or support. Now, we may have the author. Okay, let me move you to what we have in our lecture. Okay, this is going to be center. This is the C section. This is section. And then following this C section, the center locate from the top flank up to centimeter. This is going to be the top flank. And then the center locate 2 centimeter. So beware about what the problem forward you. You got to measure downward. And then this is 2 centimeter. So this is not the center. Okay, this is not the center for sure. Because it said 2 centimeter from the top. Okay, so we relocate it. This section is the same as before. is going to be one axis symmetry. Okay, one axis symmetry. So following this one, this is 2 centimeter. So the axis passing to the centroid supposed to be this x-axis. Okay, not that axis. You may elapse it if you don't like it. Okay, make us confused. And then y bar. Now y bar. Okay, y bar. Let me zoom in. The y bar is gonna be here, and that's gonna be 2 centimeter. We have another centroid over here. Okay, over here. And then they ask us to determine the moment of inertia about x-axis. Where is x? Okay, let's call this one x prime. Okay, just shift it. And we put this one for the x. And then we put this one for the y. This one for the y. And then we put this one for the axis y prime. Okay. Following this one, we've got to separate the area. Let me put this one going to be number 1. Okay. And then put this one for number 2. And then put this one for number 3. And since the section in 3D is very hard to solve it, okay, อาจารย์ recommend you to the 2D section, okay, and link it. That's gonna be 12, 14, 16. Put it for 8 centimeter. 8 centimeter. Okay, and this is gonna be 2 centimeter, 2 centimeter, and this is gonna be 12 centimeter, 2 centimeter, and 2 centimeter. And then 6, okay, that's gonna be 3 centimeter. This is gonna be the thickness. This is gonna be the thickness, and it's gonna be 3 centimeter to represent this one 6 centimeter. And this is gonna be the thickness. Then we separate first one, and then this is the third one, and then this is going to be our green. Okay, this is green. So following this one, again, we have this one measure for 1, 2, 3, 4, 5, 6, 3, and then this is 3. This is going to be our y arm, and then this is going to be our x arm. Okay, we start with this 2 axes first. Okay, to not make it confused. The first one we have it over here. Okay, so I sub x prime is going to be equal to I sub x prime 1 and plus I sub x prime 2 and then plus I sub x prime 3. So the first one we have 6 centimeter. The centroid of this one will locate half of the whole depth. That's gonna be 3 centimeter and 3 centimeter. Okay, that's gonna be this figure. Then following this dashes line, we will have this one 20 and 2 and 6. This is 3 centimeter. So that's gonna be 2 2 and then times 6 cube and then divided by 12. This is going to rotate about this axis. Okay, rotate about this axis. Then what we have kept, that's gonna be the second area. Oh, it's gonna be the distance, the distance from here to here. And this is gonna be the sub y, okay, for number 1. And then, this is 2 centimeter. So this is 3, this is 2. This is going to be 3 minus 2 equal to 1 centimeter. So we have this one plus the area, 2 times 6, 2 times 6, the area. And then we have 1 square. Then let me move to the second area here. Second area here has the width of 12, and this is going to be the centroid Hopkins. Then we have the moment of inertia about this centroid first. 12. This is 2 cube divided by 12. And then the centroid. This is going to be the sub y 2. And this is half of the depth plus 12 times 2, the area. And then over here it's going to be 1. And then square. Now, coming to the third section, you can see the third section and the first one, they are the same. 2 and then 6 cube divided by 12. The area 2 times 6, and then this is going to be the centroid, and then this is going to be 1. So you may times 2 over here. Since this orange and light blue, they are the same. Okay, putting everything together, you will get this one in centimeter power 4. I got it 128 centimeter power 4. And again, should say something. We have 1 meter equivalent to 100 centimeter. So this is going to be power 4, and this is going to be power 4. So 1 meter power 4 is going to be 10 power 8 centimeter power 4. Okay, if you like to change the unit, okay, you got to change this one. You got to divide it by 10 minus 8, and then meter power 4, centimeter power 4 per meter power 4, cut, you will get this one, 1.28 10 minus 6 meter power 4. Okay, change it to meter power 4, and then this one will be 1.28 10 power 6 millimeter power 4. Okay, you can see millimeter power 4 always small, millimeter power 4 very large. Okay, very large, and that's going to be our first one. Now we have I sub y prime. I sub y prime over here. Okay, that's gonna be equal to the first I sub y prime number 1 plus I sub y prime number 2 and then plus I sub y prime number 3. Three of them. Okay. Now let's move it over here. Sub y prime and then start with this one. The axis passing the centroid of this one going to be here. So based on this one, this is 6. Okay, 6. This is 2 cube and then divided by 12. Now, the distance difference between these two centroids is here. And then, you know, this is going to be 12 divided by 2. And this is going to be 2 divided by 2. This is going to be 1. This is going to be 6. The total going to be 7 plus area 6 times 2 and 7 square. Now, coming into this one, this is the centroid. It's on top on each other. Yes, plus this one 2. This one 12 cube. 12. About this one. About this one. And then plus 0. Plus 0. The last one. The last one. We have it over here. The last one. We have it over here. That's going to be the same as this one. Times 2. Okay. If not, you may see this, the first term, 6 times 2 cube. 12, the first one. Then the area, 6 times 2. And then from here to here, it's going to be 7 centimeter as this one. So the second one, I sub y prime 1472 centimeter power 4. Okay. And then change it. You may put it 10 power 8 centimeter power 4 meter power 4. That's going to be 14.72 10 minus 6 meter power 4. Okay, and then change it the same way. Time 10, 12, 14.70 10 plus 6 millimeter power 4. That's going to be the moment of inertia about x prime and y prime axis. And we use this a lot in our real life. Okay, our real life. How about x and y? We still have 2 more. This is going to be the axis for x and this one for the y. Wow. If you got to do it, you got to draw another pictures. Believe me, it's better. Okay. Let me take it about 10 more minutes. Okay. Let me stop this one first. Okay. Come back. Okay. We have I sub x and I sub y. I think it's better to make a copy of this one. Okay. Let's see. If you trying to make a copy of this one by 6 centimeter, okay, this is 1, 2, 3, 1, 2, and 3. And then you may move it over here, 6 centimeter, 1, 2, and 3. Now, following what we have, 6 centimeter, 1, 2, and 3. And then 6 centimeter, 1, 2, and 3. We have the width. This one we call width. Okay. The yellow and the light blue we call red. This one we call flank. Now, we put it by the same way. For this one, the reference axis is x over here and y over here. Again, this is the point we used to be the center of the section. Now, we do the same thing for the orange. Okay, this is going to be the orange. And we will start by determining it based on I sub x, based on I sub x. Then I sub x on this one gonna equal to I sub x palm plus 1 plus I sub x 2 and plus I sub x 3. For I sub x1, its centroid is over here. And then putting the parallel axis to the centroid. And this is 2 centimeter, 3 centimeter, 3 centimeter. By its own axis, it's going to be 2 times 6 cubed over 12. Then plus due to this d sub y1, the eccentricity, the area 2 times 6. What is this? This is simple. This is 3 centimeter times 3 square. Wow, that is simple. Yes, okay. And how about number 3? Okay, this is number 3. Number 3 has its own centroid over here. Own centroid over here. And then this is 2 centimeter, 3 centimeter, 3 centimeter. The first term about its own centroid, 2 times 6 cubed over 12. The area 2 times 6. And then this is going to be 3 square. So this one times 2. Okay, due to the symmetry. Then for the green, the green gonna have its own centroid over here, passing this one. Then you will have the moment of inertia. This is 2 plus 2. This is 112 times 112 cubed over 12. Due to the eccentricity from here up until here, this is d sub y2 plus 2, the area, times 12. And what is going to be, this is number 3. Number two is correct. Okay, this is number 2. What is this? This is 2 centimeter. And this is 4 centimeter, the thickness. Okay, and then half of this 2 divided by 2 is 1. So this is 6 minus 1 times 5 square. Then I sub x palm. Sorry, I sub x. Only I sub x. 96 centimeter power 4. Okay, 4. That's going to be larger than the previous 2. Now, we move to I sub y. That's I sub y1 plus I sub y2 plus I sub y3. And then for the y, this is going to be the axis. Okay, the first one going to be the axis. That's going to be 6 times this one 2 cube over 12. Okay, and then referring to this one, we have this 10 to be d sub x1. This x1. That's gonna be times plus 2 times 6. And then this is gonna be half of this one, 1 square. Okay, now coming to this one. This is gonna be, hey, this is wrong. This is wrong. This is wrong. This is wrong. Sorry for this one. This is wrong. This is about, it's not about y. This is to be for the y, for the y. For the x, this one gonna be plus 12. This is 12. This is what? This is 2 cube over 12. That's going to be about this axis. And then this is correct. Plus 12 times 2 and times 6 minus 1, 5 square. You will get this answer for sure. Okay. But for this one, you got to put it in this direction. So 2 times 12 cube. Okay, this is 2 times 12 cube over 12 plus 2 times 12, the area. Now, measure from this one. Measure from this one. You measure from this one until this one. That's gonna be sub x number 2. And then this is going to be 6 centimeter. This is going to be 2 centimeter. So times a squared. Okay. And then for the last one, we call finish our class plus the third one. Okay. About y? About this axis plus this is not going to be the same like this one. 6. Let's say this one not equal 6. This one 2 cube over 12. Now the distance from the centroid from here to here gonna be different. This is d sub x3 plus 6 times 2. And this is gonna be what? 2 times 12 times 1. That's gonna be 2. This is 2. Total here plus 12. And this is half plus 1 square. Okay, you will get this one 4,544 centimeter power 4. I believe 3 examples more than enough for you guys to be able to solve your problem number 6 in our final examination. And again, it's going to be the end of our lecture. Even though you have this one more, you can study it from my PowerPoint. And for the best wishes, I hope you guys should be able to focus on some problem, and you also can solve those kind of problem. Okay, and wish you the best luck.